One of the most significant breakthroughs in modern astrophysics, especially during the late 20th and early 21st centuries, is the emergence of a widely accepted framework for understanding the universe: the Lambda-CDM cosmological model. For generations, humanity has pondered profound questions regarding the cosmos, such as its nature, composition, extent, origins, age, and the processes that have shaped it into its current form. We have also speculated about its eventual fate. Thanks to unparalleled advances in astronomy, including detailed measurements of galaxies across different epochs of cosmic history, comprehensive sky imaging at microwave wavelengths, and observations of numerous supernovae and other transient events, we now have conclusive answers to these long-standing mysteries. The universe is composed of roughly 68% dark energy, 27% dark matter, and just 5% regular, visible matter. It originated from an incredibly small, dense, and almost perfectly uniform state around 13.8 billion years ago in a hot, explosive event known as the Big Bang. Since then, the universe has been expanding, cooling, and evolving under gravitational forces. At least, this is the broadly accepted theory. However, the James Webb Space Telescope, JWST, with its groundbreaking infrared capabilities, has begun to challenge many of the assumptions we held about the early universe. Rather than merely observing the formation of a few small stars, a scenario that fits well with our hierarchical structure formation models, the JWST is sending back data that presents serious challenges to the current understanding of cosmic origins. As it peers deeper into space, the telescope reveals unexpected anomalies that question long-standing theories about the universe's development. The findings also illuminate profound scientific and philosophical questions. In particular, the JWST has captured evidence of galaxies that appeared much earlier than scientists had predicted. This suggests that the universe was forming galaxies much more rapidly and in a way that current theories cannot fully explain. To put it in perspective, it's like witnessing characters from a story who are far younger than they should be based on the timeline, or walking into a nursery to find not infants, but teenagers, an unsettling surprise. This unexpected discovery could have far-reaching implications for cosmology. If these observations hold, it might mean that our current understanding of galaxy formation and the evolution of cosmic structures is incomplete or even incorrect. The existence of these galaxies challenges our models, and astronomers may need to revise their theories to account for these faster-than-anticipated formations. One potential explanation is that these galaxies formed in ways different from those closer to us, perhaps through an unknown mechanism that allowed the rapid growth of massive galaxies. Another possibility is that these galaxies formed as a result of exceptionally fast mergers of smaller galaxies early in the universe's history, which would require significant revisions to the current models. The discovery made by JWST is an extraordinary development in the study of cosmic evolution and galaxy formation. It is likely to inspire astronomers to propose new theoretical models and seek additional observational data to better understand the universe's history and the properties of these enigmatic distant galaxies. Importantly, the discovery of these unusually large galaxies was not an isolated incident. For years, scientists believed that early galaxies, formed just after the Big Bang, roughly 13.7 billion years ago, were too fragile to exhibit complex structures like spiral arms, bars, or rings. Such features were thought to have developed later, around 6 billion years after the Big Bang. However, another fascinating study using JWST data has shown that these delicate structures could have emerged as early as 3.7 billion years after the Big Bang, a time close to the universe's infancy. As Christopher Canales, an astronomy professor at the University of Manchester in the UK, and co-author of the study, explained, this finding forces astronomers to rethink the way they understand the formation of early galaxies and the process of galaxy evolution over the last 10 billion years. This new insight follows the announcement of a different study, based on JWST's data, revealing that early galaxies produced far fewer heavy elements than scientists had previously anticipated. While we now know that early galaxies had fewer heavy elements than expected, the relationship between a galaxy's chemical composition and its structural evolution remains unclear. Historically, much of our understanding of galaxy evolution was based on data gathered from the Hubble Space Telescope, which, despite its remarkable achievements, lacked the resolution to probe certain details. In contrast, JWST's high-resolution observations of distant galaxies reveal that some of these early galaxies, despite their youth, already exhibited well-defined structures, much like our own Milky Way. This breakthrough was based on the analysis of 36 galaxies, a sample size that represents the largest set studied so far using JWST data. As Leonardo Farah, an astrophysicist at the University of Victoria in Canada and the lead author of the study, put it, for over 3 decades, scientists have believed that disk-shaped galaxies were rare in the early universe, given the frequent violent interactions that galaxies experience. The fact that JWST has observed so many of these disk galaxies suggests that their structures formed much earlier than anticipated, revealing just how powerful this telescope truly is. According to the new study, researchers classified nearly 4,000 early galaxies by their shape, including disks, point sources, and spheroids. These galaxies were further categorized based on whether they exhibited smooth or structured features, with the latter group showing signs of star formation bursts and mergers. The results suggest that well-defined structures, such as disks, formed far earlier than scientists had thought, challenging previous assumptions about the pace of galaxy evolution. Beyond these findings, the JWST's observations have raised questions about one of the most fundamental aspects of cosmology: the rate at which the universe is expanding. This is known as the Hubble constant. There are 2 primary methods for calculating the Hubble constant. One based on observations of the early universe, like those made by JWST, and another based on the observation of nearby stars in the current universe. Despite years of research, these 2 methods continue to yield different results. Initially, scientists expected these discrepancies to resolve as data improved, but even with more precise measurements, the discrepancy persists, raising questions about the model itself. Recent data from JWST has only deepened this issue, suggesting that the inconsistency may stem from a flaw in the model, rather than errors in the data. This persistent anomaly has led some scientists to question whether the Big Bang theory itself is in need of revision. As Dr. Duke Barnes, a postdoctoral researcher at Western Sydney University, points out, it's possible that the Big Bang will eventually become part of a larger, more comprehensive narrative. Just as Nicholas Copernicus' heliocentric model didn't completely dismiss earlier ideas, but rather refined our understanding of planetary orbits, we may one day refine our understanding of cosmic origins to include events that occurred before the Big Bang. The Big Bang theory is not without its critics. Since its inception, many have raised objections, highlighting several challenges that need addressing. One common criticism is that the Big Bang violates the first law of thermodynamics, which states that matter and energy cannot be created or destroyed. Critics argue that the theory suggests the universe began from nothing, but proponents counter that the Big Bang theory focuses not on the creation of the universe, but on its evolution. Additionally, since scientific laws break down at the moment of the universe's creation, there is no reason to believe the first law would apply in this context. Another criticism comes from the law of entropy, which suggests that systems tend to become more disordered over time. Critics argue that the formation of stars and galaxies contradicts this idea. However, proponents of the Big Bang suggest that if the early universe was homogeneous and isotropic, the current universe shows signs of adhering to entropy laws. Some astrophysicists and cosmologists believe that certain evidence, such as the redshift of distant galaxies and cosmic microwave background radiation, has been misinterpreted. They point out the absence of exotic cosmic bodies that, according to the Big Bang theory, should have emerged early on. Others take issue with the inflationary period of the Big Bang, arguing that it violates the principle that nothing can travel faster than light. In response, some theorists suggest that during the Big Bang, relativity did not apply, so there was no limit on the speed of expansion. Others argue that space itself can expand faster than light without violating the laws of physics. In response to these challenges, alternative models of the universe's development have emerged. The steady-state theory posits that the universe has always existed in a consistent state, with new matter forming as the universe expands. The Big Bounce theory suggests that our universe is part of a cycle of expansions and contractions. The eternal inflation theory envisions a vast multiverse where our universe is just one of many bubbles. Despite the presence of these competing theories, the Big Bang remains the most widely accepted model due to its ability to explain many observed phenomena. While not perfect, it provides the most comprehensive explanation based on current evidence. However, it is clear that our best model is far from complete, and future discoveries, possibly from the JWST, may reveal a more complex and stranger truth about the origins and evolution of the cosmos. The James Webb Space Telescope represents a monumental leap forward in our understanding of the universe. By uncovering new details about the cosmos, it challenges established ideas and opens up new avenues for exploration. With its unparalleled infrared capabilities, the JWST has provided unprecedented insights into the early history of the universe. It has revealed galaxies forming much earlier and more quickly than current models predicted, forcing us to reconsider how galaxies evolve. Furthermore, the JWST has refined our understanding of the chemical composition of early galaxies, showing that they produced fewer heavy elements than expected. This has implications for our understanding of how galaxies evolve and enrich their environments with the elements that are crucial for life. The JWST's study of the Hubble constant has also deepened the mystery surrounding the universe's expansion rate. Its measurements of the early universe suggest a different expansion rate than those based on observations of nearby stars, highlighting the need for a re-evaluation of our understanding of cosmic expansion. In addition to these breakthroughs, the JWST has provided new insights into the cosmic microwave background radiation, offering clues about the universe's early history and the formation of galaxies. With its cutting-edge technology, the JWST is providing clearer, more detailed images of distant objects, pushing the boundaries of what we can observe in the cosmos. Looking ahead, the JWST's mission promises to continue unraveling the mysteries of the universe. Its observations will explore a wide range of topics, from the search for exoplanets to the study of planetary systems and the origins of life's building blocks. In sum, the James Webb Space Telescope is a triumph of human ingenuity and scientific collaboration. By expanding our knowledge of the universe and challenging existing theories, it has opened a new chapter in our quest to understand the cosmos and inspired future generations to continue exploring its mysteries. The advancements made by the James Webb Space Telescope are not just pushing the boundaries of astrophysical observation, but are also revolutionizing the fundamental questions about the origins and structure of the cosmos. These discoveries could potentially reshape not only cosmology but also the entire field of astronomy. As scientists continue to delve deeper into the mysteries of the universe, the new data provided by JWST offers an opportunity to revisit, refine, and sometimes overhaul our theoretical frameworks. The notion of cosmic evolution is now being viewed in an entirely different light. The early formation of galaxies, which was once believed to have been a slow and gradual process taking billions of years, might actually have occurred far more rapidly than we ever anticipated. The implications of this are enormous. If galaxies can form and develop structures much earlier than previously thought, it opens the possibility that there were additional, unknown processes at play during the universe's early years. Processes that enabled the rapid accumulation of matter and the formation of large, complex structures in a fraction of the time we once thought. This could mean that our theories about galaxy mergers, star formation, and dark matter may be incomplete. More research is needed to investigate whether these early galaxies formed in isolation or through rapid mergers, which may have contributed to their large sizes. Understanding how early galaxies formed and grew in the first few 100 million years of the universe will be crucial for refining models of cosmic history.